Welcome back. In video 3, I'm just going to do some examples. So this first one, we're going to let r be a real number such that the absolute value of r is less than 1. So it could be negative 0.5 or 0.5, stuff like that. Prove the following statement using induction. So for all n in the naturals, the summation from I equals n to infinity of r to the I is r to the n over 1 minus r. Okay? All right. So let's look at a proof. So proof using induction. So our first step, base case. Okay, so who do we look at? We're going to look at n equals 1. That will be our base case. All right, so on the left-hand side, we have I equals 1 to infinity of r to the I. And so this is a mistake that a lot of people make. They'll write equals, and then they'll plug in 1 for n over here. But we can't do that. That's assuming what we're trying to show. Okay, so what is this? Maybe you remember, maybe you don't. From calculus, this is our geometric series. So, and we use this one because the absolute value of r is less than 1. So we have r over a nice r, geometric. Okay, cool. Well, fun fact, r to the 1 over 1 minus r is also r over r, 1 minus r. Therefore, we're done. Or you can say they're equal, so we're done. Okay? All right. So inductive hypothesis. Assume for k in the naturals that the summation from I equals k to infinity of r to the I equals r to the k over 1 minus r. Okay? All right. So now inductive step. First, I like to start with what we want. Okay, so I want to show that summation from I equals k plus 1 to infinity of r to the I is equal to r to the k plus 1 over 1 minus r. Okay. So for me, I prefer summation instead of multiplications. So I'm going to start with this side. And I'm going to say consider, okay, so I'm just considering the left-hand side. And then hopefully I say a bunch of true things, one of which involving my assumption from the inductive hypothesis. And then I get the right-hand side of what it is that I want. Okay? So since this is summation, what I'm thinking about is this looks like r to the k plus 1 plus r to the k plus 2 plus ... forever and ever and ever, right? So that's what this looks like. So in my inductive hypothesis, I have something that looks like this. So it also looks like something like here, down here, but it's going to start with r to the k plus r to the k plus 1, blah, 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 blah. So we're going to use something tricky here, okay? We can always add 0. So 2 tricks you're going to want up your sleeve all the time is you can always add by 0 and you can always multiply by 1, just in a tricky way, okay? So here I'm going to rewrite what I already had. And now I'm going to add r to the k because this is what's going to give me this guy up here. But I can't just add that out of nowhere, right? But I can add 0. So how can I turn this into 0? Well, I can just minus by r to the k. All right. So now we're doing good. So I'm going to rewrite. I'm going to combine these two pieces here. And now I just have this minus r to the k. Okay, awesome. So now I get to use my inductive hypothesis. Okay, I go up here, I look at my assumption that I had. Okay, well this should equal r to the k divided by 1 minus r. So I get to write that. So r to the k over 1 minus r to the k. Okay, so we're going to have to use the other trick that I talked about, which is we can always multiply by 1. So, and this is just like finding a common divisor. Okay, so I'm going to multiply this by 1 minus r divided by 1 minus r. Okay, so now we get r to the k over 1 minus r minus r to the k minus r to the k plus 1 over 1 minus r. Awesome, so now we have, so I'm going to distribute this negative to help us out a little bit. There we go. So now we have r to the k plus 1 over 1 minus r. Okay, is that what I wanted? We can look up and check. Yes, that is. Perfect. Awesome. So now we're done. We're done with our proof. Well, yeah, hopefully you were like, whoa, Danica, you didn't write a conclusion yet. You have to write a conclusion. That's what you taught us. And please don't forget to say that you're doing it by induction in your conclusion. Okay, awesome. Okay, so now this next example isn't induction. I just wanted to show proving one statement 3 different ways that we've talked about before induction, okay, because we can't forget the other ways. So direct, contrapositive, contradiction. Okay, so the statement we're trying to prove is let x, y be in z, be in the integers. If x and y are odd, then x times y is also odd. Okay, all right, so let's break it down into like statements. So let's let P mean that x is odd, Q means that y is odd, and then R is that x times y odd. Okay, so our original statement is going to be is that P and Q implies R. Okay, all right, so all we're proving is odd times odd equals odd. So we can't use that in our proof, okay, if that makes sense. And that may sound really obvious, but sometimes that really does trick up students is accidentally using what they're trying to prove in their proof, okay? All right, so let's start with a direct proof. A. So a direct proof would just be us just talking about their definitions and just boom, 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 boom. Let's talk about, assume that P and Q are true, and then we'll show that R has to be true. Okay, so since x and y are odd, then there exists a k and an l in the integers such that x equals 2k plus 1 and y equals 2l plus 1. Okay, so now let's just multiply those together. Okay, cool. So what is it we're trying to show? We're trying to show that x times y is odd. So for something to look like they're odd, it has to be 2 times some integer plus 1, or maybe minus 1. Okay? So I notice I can pull a 2 out. And boom, we got it. So all we have to say is, since k and l are the integers, then 2kl plus k plus l is in the integers. Therefore, by definition, xy odd. Cool. Okay. So now what's next? Contrapositive. So hopefully you remember what contrapositive means. So if we have our original statement is P and Q implies R, contrapositive is, so if this is our original statement, then the contrapositive is going to be not R implies not P and Q. Okay, so what's not P and Q? That means, so not R not P or not Q. Okay? So remember, we flip-flop them and then negate both of them. Negate the statements on either side. Okay? All right, so we're trying to show this. All right, proof. Assume x times y is not odd, so x times y is even. So now that I'm going to approach it like a direct proof. So then there exists, let's say, an m in the integers such that x times y equals 2m. Okay? Cool. Loss to generality, we have 3 cases. One of them is odd, the other one's even. They're both odd or they're both even. Okay? So without loss of generality, so all that means is if I say that x is even and y is odd, that's basically the same as saying y is even and x is odd. Okay, because they're just variables. I just flip-flop them. We have 3 cases. So let's start with the one where they're both even. Case 1, x and y even. Then there exists KL such that x equals 2k and y equals 2L. So x times y equals 2 times 2LK. Okay, so that works out. So we're all good. All I'm doing is I'm checking like, oh shoot, no, I'm doing this wrong. Okay. So this is why I talk about what I want sometimes, because sometimes you can get caught up with saying a bunch of true things, and they are true, but maybe they're just not getting you anywhere, okay? So I'm just trying to show that one of them is even. And then if one of them is odd, if both of them are odd, then the whole thing breaks down, okay? So that's what it means. So I'm assuming that this one is true, and then I want to show that when this is true, this one's also true. So what does that mean? So not P or not Q means x is even or y is even. And it could be that both are even. Okay. So let me erase this. X and y even. Then we're done because one of them's even. Then done since one's even. So what I mean is, maybe this is not possible. I mean, it is. We just showed it is. But it doesn't really matter to me because I show that this statement is true if this case happened, okay? So case 2 is x even and y odd. So it's the same as above. We're done since x even. Or since not P is true, okay? So case 3 is when we actually have to do a little bit of work. So case 3, x and y odd. So now this is saying that not P or not Q is a false statement. So we want to show that this cannot possibly happen if x times y is even, okay? So this is basically the same thing as before. So I'm going to cop out and I'm going to say repeat argument above in part A. To show x times y not even in this scenario. Okay, so now I've shown it true, okay, because case 3, I show that that's not even possible. So this case, not possible. Therefore, if x times y even, then x or y even. Ooh. Boom. Roasted. Okay, cool. So the next one is contradiction. So let's recall what the negation of an implication is. Okay, so if I have P and Q implies R, how do I negate this? Please pause this and make sure that you remember this. This is so vitally important for the rest of your mathematical career, including this class. Okay, what do we get? We end up getting P and Q and not R. Okay? Cool. All right. So contrapositive proof, oh, sorry, not contrapositive, contradiction. Proof by contradiction. Assume x and y odd and xy even. Okay, so this, once again, is going to be kind of like the direct proof. Okay, so I just sped through some of it. So we're using our assumption that x and y are both odd. And so now I've shown through this that therefore x times y is odd. But what's the matter with that? Well, we assume that x times y is even, and you can't be both. Okay, there's my C with the exclamation point that I love. All right, so that's all I have right now. Thank you very much. I hope this is all coming together for you. Have a good one.